All right. Well, we have Amitesh Datta visiting from Princeton, and he will tell us about classifying plane curves and symplectic form manifolds using Braid groups, the symplectic, isotopic, conjecture, and CP.
Thank you so much, Adam, and thank you for the introduction and for the invitation. Hello. So I'm really excited today to tell you a story about the dichotomy between symplectic geometry and algebraic geometry in 4 dimensions. And the story will involve ideas from the theory of plane curves from the perspective of algebraic geometry and symplectic geometry. It will involve ideas from algebraic topology, specifically monodromy theory, and it will also involve ideas from geometric group theory, specifically the word and conjugacy problems in the Braid groups. So we're going to see ideas from many different areas of math and how they connect together. And along the way, I'll also talk about my work. But the talk is designed to be super accessible and no prior background is assumed. So I hope that whatever angle you're coming at, you will get something from the talk. So to start off the story, we need a fundamental motivating question. So the question is the following. It's based on the inclusion of 2 worlds. So we have the world of complex projective surfaces, and we have the world of closed symplectic form manifolds. Okay, so we have these 2 worlds. And though we're going to start the talk by motivating based on this question, we aren't really assuming any background on symplectic geometry or algebraic geometry. This is the algebraic geometry world. This is the symplectic geometry world. Very formally, we can think of a complex projective surface as a triple of data. It's a real form manifold M with a symplectic form omega and a complex structure J compatible with omega. And a closed symplectic form manifold is just a real form manifold M with a symplectic form omega. So you can see that we're forgetting the complex structure. We can get a closed symplectic form manifold from a complex projective surface. And a fundamental question in 4-dimensional topology is when can you go the other way? So when can you put a compatible complex structure on a closed symplectic form manifold? So that's going to be the main motivating question of the talk. When is a symplectic form manifold a complex projective surface? When is a symplectic form manifold a complex projective surface? Okay, so that's the question that we're going to focus on. Now, what I'm going to do is I'm going to reduce this question. Yes?
So you only worried about the complex surfaces up to diffeomorphism?
Yes. That's right. Yeah, so okay, I mean, another point is if there are questions, just please always feel free to interrupt me. So what I'm going to do is I'm going to first discuss how this in principle reduces to the theory of plane curves. And then I'm going to talk about how we can use Braid groups to study these questions. Okay, so let's first talk about the plane curve picture. So the plane curve picture starts off with Zariski, and it goes as follows. So let's start off with a complex projective surface X. Okay, what we're going to do is we're going to assume this technical condition. I'm not going to talk much about it, but you just assume that the homology class of the Kähler form, of the symplectic form on X, is integral. So we have a complex projective surface X. And let me know, I'll try to avoid writing the bottom if people can't see, but you have this X. Zariski showed that you can find these branched coverings of X over CP2, where the branched curve is some algebraic curve in CP2 with only nodal and cuspidal singularities. So it's a nice branch covering. And what I mean by branch covering is it's a D to 1 covering. So D points in X map to 1 point in CP2, except along the branch curve. So along the branch curve, it's 1 to 1. Okay, and so this is a D to 1 branch covering of X over CP2. The principle is intuitive. What you do is you want to take your complex projective surface X, use the Kadera embedding theorem to embed X in some complex projective n space, and then you take a suitable projection onto CP2, a generic choice of projection onto CP2, and that will realize X as a branch covering over CP2 with only cusps and nodes in the branch curve. Okay, so this is what Zariski proved, and then there's
actually that's way before Zariski. I mean,
oh really? Okay.
Yeah, if you start out, that's classical Italian geometry.
Yeah.
You start out with a surface in projective space.
Yeah.
This is way before Darman. Then you just project down as you say.
Okay. Oh, I saw it attributed to Zariski somewhere, but anyway, thank you for the comment. Yeah, I guess I will. Yeah, maybe I'll talk about this with you after as well. So there's a conjecture of Chisini. So Chisini's conjecture is that, so we want to try to understand X from the branch curve. That's the idea. And Chisini conjectured that in fact, except in a finite list of exceptional cases, the branch curve determines X. The conjecture of Chisini is that D determines X except in a finite list of exceptional cases. And it was proven by Kulikov, this is the theorem of Kulikov, that, for example, if the degree of the branch covering is at least 5, so if it's sufficiently large, if little d is at least 5, then in fact D does determine X. The branch curve determines X. D determines X.
So really you mean D comma little d determines X. Two D's together?
I think it's just the branch curve D.
Well, could you take a threefold cover and a twofold cover? The same. I just set y cubed equals the equation cutting out d and y to the fifth. Like it's CP2, d is going to be cut out by the one equation.
Yes.
For hypersurface.
Yes.
And I could make a curve by saying y to the n is equal to f or f.
Oh, okay, I see. Okay, so you're saying that the branch curve and the degree of the branch curve.
Yes.
Okay, yes, that's right. Yes, that determines X. Yes, that's right. Yeah, thank you. Yeah, so that's the theorem of Kulikov. Okay, so in principle, we can study the complex projective surface by studying the branch curve. So that's the takeaway from this discussion. And Aru basically did the similar construction in the world of symplectic geometry. So what Aru proved is that if you have a symplectic 4-manifold X, X4 omega, you can find these branch coverings of X over CP2, Fk, over CP2. And these are parametrized by the positive integers. Okay, so this is a family of branch coverings parametrized with the positive integers. The branch curve is some symplectic curve in CP2, again with only like nodal and cuspidal singularities. And Aru showed that Fk is canonical up to isotopy. So Fk is canonical up to isotopy for sufficiently large k. Canonical up to isotopy for k sufficiently large. Okay, so this is doing what we just talked about in the algebraic geometry world, in the world of symplectic geometry. And because of the fact that Fk is canonical up to isotopy for k sufficiently large, we can get interesting symplectic invariance of X from the isotopy classes of the dk. So if you isotope the branch covering, the branch curve will also isotope. But you can also create or cancel nodes in the branch curve. So there's an extra thing you can do to the branch curve. And so what we get is that because the fact Fk is canonical up to isotopy for k sufficiently large, the isotopy class of dk up to node creations and cancellations is going to be, and up to node creations and cancellations is a symplectic invariant of X for k sufficiently large.
What is K again?
So K is like the family of symplectic branch coverings is characterized by K. You can basically, okay, so what does K mean? The pullback of the Fubini study form on CP2 is K times the symplectic form on X. Okay, so this is like a theorem of Aru. And so we have a similar like situation in the algebraic geometry world. And what's really cool is we have the following takeaway, is this question I talked about. When is a symplectic 4-manifold a complex projective surface? In principle reduces to a question about plane curves, because we have the following statement that X, a symplectic 4-manifold X is a complex projective surface, if and only if the branch curve dk is isotopic to an algebraic curve up to node creations and cancellations. Isotopic to an algebraic curve in CP2. So in principle, understanding when a symplectic 4-manifold is a complex projective surface comes down to understanding when these symplectic curves in CP2 are isotopic to algebraic curves. And so now we have like a plane curve problem, and this is abstractly like referred to as a symplectic isotopy problem. So the symplectic isotopy problem basically asks, so this is what we call the symplectic isotopy problem. Symplectic isotopy problem asks, when is a symplectic curve in CP2 isotopic to an algebraic curve? So when is a symplectic curve in CP2 isotopic to an algebraic curve? Isotopic to an algebraic curve. Okay, so that's the question we're now interested in. Now, this is actually a very fundamental question, even from the perspective of low-dimensional topology. So even if you're not interested in symplectic geometry and algebraic geometry, of course, I'm talking about a symplectic curve. This is a real surface. And so a real surface in CP2, understanding the isotopy problem for them, is one dimension level up from knot theory, when we study co-dimension 2 isotopy in three-dimensional space. And we're now asking a fundamental question: when are real surfaces, when can you isotope them to satisfy a polynomial equation? So this is a very natural question. We're talking about this question essentially in the symplectic isotopy problem. But now, I'm sort of not going to talk about, I'm going to try to give you a combinatorial model of symplectic curves so we can think about this very topologically. So the combinatorial model is up on the board, and I'm going to read through it so you don't have to worry about reading through it immediately. But what we do is we take...
So I have a question.
Yes.
So when you do this isotopy,
Yes.
does the Fubini-Studi, does the standard 2 form have to always be non-degenerate on the curve?
Yes, that's right. It has to be a symplectic isotopy. That's right.
Okay.
Yeah, that's a good question. Yeah, thank you. All right, so what we're going to do is we're going to look at like a special form for our symplectic curve or our surface in CP2. We take a projection, a linear projection of CP2 minus a pole to CP1. So you just forget one. You can imagine like forget a coordinate, forget the last coordinate. So this is well defined once you delete a point at infinity. So we get a linear projection from CP2 minus a pole to CP1, which I've drawn on the board. And the fibers of the projection, these are we call the projection pi. The fibers you're sort of visualizing as these complex lines, okay? And now what you do is you want to define this thing, which we call a simple Hurwitz curve in CP2. It's an oriented two-dimensional real submanifold of CP2, and it intersects the fibers of pi positively and transversely everywhere except on a finite set. And the finite set consists of non-degenerate tangencies to the fibers of pi and nodal and cuspidal singularities. So it can have singularities just like our branched curves, which are nodes and cusps. And I'm going to sort of draw a visual depiction of such a thing. So you kind of can sort of see here. This is kind of an example, like just a visual, like real picture, where you sort of see you have these cuspidal singularities, you have these non-degenerate tangencies to the fibers of the projection. The fibers are vertical, and you have these nodes and you have these cusps. Okay, so this is a model. This is what we call a simple Hurwitz curve in CP2. Okay, and now it's a fact that any symplectic curve in CP2 I can isotope. If it has nodes and cusps only, I can isotope it to satisfy this model, and vice versa, any simple Hurwitz curve in CP2 can be isotoped to be a symplectic curve in CP2. So to study the symplectic isotopy problem, we're just going to study the isotopy classes of surfaces with this nice property, and that's going to be what we're going to do in this talk. Yes.
Could you explain why it's a submanifold if it has nodes?
Oh, so I mean, yeah, we require like, around nodes, we're not strictly saying it's a submanifold, but there's a local model for the singularity. So around a node, we'd sort of say like z squared equals w squared. It's modeled, yeah. And around cusps, it's z squared equals w cubed. Adam? Yeah.
But so basically, the one thing that you're ruling out is that it can't have any negative transverse intersections with the fibers.
Negative transverse.
Right, when you're saying that it intersects the fibers of pi positively and transversely. Okay, but except sometimes it's not transverse, it's tangent, and right, that's the non-degenerate tangency, but also it can't have negative intersections.
So are you asking like what's the restriction on these kinds of things? So
Yeah.
It can have higher order tangency.
Right, or higher order tangency.
You can do a perturbation to get rid of that, but I think the main restriction is that it has a finite number of these. That's right. All right, so let me erase this. So it's generally this is generally a very subtle problem. It's conjectured that if the singularities of the curve are not too bad, then this should be true. But for example, Moiseson constructed examples of infinitely many degree 18 curves with 81 cusps that are not isotopic to any algebraic curve. So symplectic curves, or if you like, satisfying this model, that you cannot isotope to be an algebraic curve. So in general, the symplectic isotopy problem fails. It has a negative answer. But there is a conjecture, which is the symplectic isotopy conjecture, that, for example, if the curve is smooth, so you assume that there are no singularities except for, in this model you just have non-degenerate tangencies to the fibers, then it should be isotopic to an algebraic curve. The conjecture is that a smooth symplectic curve in CP2 is isotopic to an algebraic curve. Smooth symplectic curve in CP2 is isotopic to an algebraic curve. Okay, so that is a symplectic isotopy conjecture, and what I'm going to do in this talk, so now we just set the stage for the rest of the talk, I'm going to explain how I developed a new theory in the Braid groups to establish an array of results on the symplectic isotopy problem and the symplectic isotopy conjecture purely algebraically. So the traditional approach to establishing these kinds of results is via Gromov's theory of J-holomorphic curves. So in 1985, when Gromov introduced this theory of pseudoholomorphic curves, he established some special cases of this conjecture. So you can define the degree of a curve. If you have a curve C, you can define the degree to be the algebraic intersection number of C with a line in CP2. Okay? And then Gromov showed that if the degree of the curve is 1 or 2, then the conjecture is true. A smooth symplectic curve of degree D is isotopic to an algebraic curve. This is when he developed his theory of pseudoholomorphic curves. It wasn't until 20 years later, around 2005, that someone refined Gromov's techniques to extend this a bit. So that was Sikarav. Sikarav showed that if the degree of the curve is 3, then a smooth, symplectic curve of degree 3 is isotopic to an algebraic curve. And then it was later extended to degree up to 6 by Shevchishin. And then shortly thereafter, Siebert and Tian proved that the conjecture is true for degree C up to 17. So this was a result of Siebert and Tian, that a smooth symplectic curve of degree D up to 17 is isotopic to an algebraic curve. So that's the state of the art, but everything is based on Gromov's theory of pseudoholomorphic curves. And what I'm going to do now is try to put this problem into the realms of algebra and Braid groups. And that's going to be the next chapter of this talk. And the talk is compartmentalized, so you can even follow the next chapter independently of what we just talked about.
Sorry, what was the n equals degree equals 18 results that you mentioned a couple minutes ago?
Oh, that was with 81 cusps. So this is just for like smooth curves.
I see. Okay.
Yeah. So actually,
it's open, but the smooth is open for 18 and up. Is that the?
Yeah. So the literature, the best result is up to 17. That's right. Yeah. But for smooth curves, like once you have cusps, then it's known to fail. All right. So let's get into Braid groups. So this is a really beautiful thing. It's not going to go into the realms of algebraic topology. So how are we going to study this? So what we do is we take one of our simple Hurwitz curves. So I'm just going to sort of draw some model for it that we sort of talked about earlier. So you have these non-degenerate tangencies to the fibers, these nodes, and these cusps. So how do we study such a curve, right? How do we study the isotopy class of such a curve? So we're going to look at it very algebraic topologically. We take our projection pi from CP2 minus a pole to CP1, and what we do is we restrict our projection to our curve C. So pi restricted to C is a map from C to CP1, right? It's going to project C down onto CP1. And if the degree of C is D, then this is going to be a D to 1 branched covering. If degree of C is D, then pi is going to be D to 1, except along these ramification points, which are non-degenerate tangencies, cusps, and nodes. So when you have like a non-degenerate tangency, two branches of C are going to come together. So you're going to have less than D points on the fiber of the projection of that non-degenerate tangency to CP1. In general, it's the same for like nodes and cusps. So if you kind of enumerate all the projections of these nodes, cusps, non-degenerate tangencies in C, P1 through Pk, then outside of P1 through Pk, there will be D points on C above every point on CP1. And along P1 to Pk, there will be less than D points on C above a point in CP1. And so what we want to do is we want to understand these ramification points. And for that, we're going to introduce this classical idea of monodromy. Okay, so how does that look like? So we look at a loop gamma inside pi 1 of CP1 minus our points P1 through Pk. So these are the projections of the non-degenerate tangencies, nodes, and cusps onto CP1. And we want to understand what happens. This gamma is living inside, maybe I'll do it on the next board so that I don't write it down too low. But gamma is going to live inside CP1. What happens when we move around gamma? What does the monodromy look like? So if we move around gamma, so if we draw gamma inside CP1, because gamma avoids all the p's, each point on gamma is going to have d points on the curve above it, right? And as we move around gamma, these d points on the curve are going to live in C, a copy of the complex line, which is the fiber. And as we move around gamma, they're going to trace out something. And if you're familiar with braids, you'll kind of see that this looks very much, or this is basically a D braid that goes from the D points at the base point all the way around. But I'm going to make this very precise. So how does this look like? So each point on gamma has D points in C above it. We have to identify each fiber with C. Now, the bundle pi from CP2 minus a pole to CP1 is not trivial. It's actually the dual of the tautological line bundle. So we have to trivialize it over an affine open subset, delete a point at infinity in CP1, and then you can identify each fiber with C. And once we've identified each fiber with C, we look at the space conf D of C. So conf D of C is basically the set of unordered tuples of D distinct points in the complex plane. So unordered tuples Z1 through ZD, where each of them is distinct from each other and they're all complex numbers. And any point on gamma is going to give us a point in conf D of C. And as we move around gamma, we're going to get a loop in conf D of C. So what does a loop in conf D of C look like? It's basically just a game of musical chairs. As sort of like a quick interpretation of this. So how does that work? We sort of simply imagine a point in conf D of C is like D points in the plane that are distinct. And we can imagine that as like D of us in this room. So you have like D distinct points. And then we just play a game of musical chairs where basically we all move around and we sit back down in some permutation of our seats. That's just a loop in conf D of C. It's a boring game of musical chairs because all of us will win, but it's still a game of musical chairs. And you can represent it geometrically as well. If you imagine like the path of each person as time varies, you sort of trace it out as a strand going upwards, where the upward direction is like the time axis, that's the z coordinate. As we kind of play our game, like the strands are going to go from top to bottom, and they're going to entangle with each other, which corresponds to us like moving around each other. And that picture over there represents something in pi 1 of conf D of C. It is nothing other than what we call a geometric D braid. D strands going from bottom to top. D points on the z equals 0 plane to D points on the z equals 1 plane. And BD is just going to be the fundamental group of conf D of C, which is also going to just be equal to all the so-called geometric D braids up to isotopy. So geometric D braids up to isotopy. Okay, so that's going to be the braid group. And our monodromy, any loop inside this pi 1 is going to give something in the braid group. So we can think of our monodromy as being a map. So the monodromy of C is a map from pi 1 of CP1 minus the P1 through PKs to the braid group BD. Okay, now that's the monodromy of C, and that's also a lie because, yeah, Lenny?
You removed the points, right? If you want to realize this.
Yeah, I removed a point infinity, yes.
So does that show up as, are you keeping track of that in the monodromy somewhere?
We will, yeah, so, okay, so you're talking about the CP2 minus a pole to CP1? Yeah, I mean, basically you can isotope the curve to avoid that point. So we can just like...
No, sorry, the CP1.
Oh, the CP1 minus a point. Okay, I see.
So you got rid of the point of infinity.
Yes.
But there's possibly some monodromy around that?
That's a good point. So that's something we will get to next. Okay, yeah, that's a good point, yes. Yeah, okay, so we have this map from pi 1 of CP1 minus P1 through PK to BD. And it's a monodromy of C, but it's only well defined up to a choice of trivialization of the bundle, which Lenny was just referring to. And a different choice of trivialization of the bundle will identify with the fibers differently with C, but that will result in an overall conjugation on the braid group BD. So the monodromy of C is a conjugacy class of maps from pi 1 to BD. Okay, so it's an entire like family of conjugacy classes of maps from pi 1 to BD. That's the monodromy of C. That's the algebraic topological information captured by the monodromy. And then there's a question, can we understand the isotopy class of C from the monodromy? And the answer is yes. And this is a theorem of Kharlamov and Kulikov. So I will give you an intuitive like description. I mean, it's not, it's a short argument. But basically, like, if you know the monodromy of C, you should know the isotopy class of C. So this is a theorem of Kharlamov and Kulikov. And the principle is basically that if you take a union of a small number of disks containing, small disks containing the PJs, then outside of that union in CP1, the monodromy is basically telling you what the isotopy class of the curve is. Then you have to glue in at those disks. Those are like these singularities, these nodes, cusps, and non-degenerate tangencies. In the topological category, it's not difficult. In the smooth category, you have to do some work to make sure everything works out well. But this is what Kharlamov and Kulikov did. And they proved that the monodromy of C uniquely determines the isotopy class of C. Monodromy of C uniquely determines the isotopy class of C. Uniquely determines the isotopy class of C.
The symplectic isotopic class?
Yeah, the symplectic isotopic class of Z, that's right. That's the theorem of Kharlamov and Kulikov, and so in principle we're reduced to studying Braid groups now. We're in principle reduced to studying these conjugacy classes of maps from pi 1 into the Braid group. Now, historically these have been very hard to understand because we need some kind of, we're trying to understand conjugacy classes of, k-generated subgroups in BD because the fundamental group is free here of rank k, so we're looking at subgroups of BD generated by k elements up to conjugacy. So what I'm going to do is try to give you some insight into this problem and tell you the results I have when actually characterizing that monodromy purely algebraically. So before I do that, I'm just going to take a quick 1-minute intro to Braid groups, just what we need notation-wise to continue. And it's essentially this result of Artin, that if you have the Braid group BD, there is a nice algebraic representation as a finite presentation. So you have this geometric picture, but Artin also proved that you can find a finite generating set, sigma 1 through sigma d minus 1, so that every braid can be written as a word in the generators, and every relation can be generated by these so-called Artin relations. And what are the generators? So the generators look like the following. You have sigma 1, where you're basically drawing d strands that go from bottom to top. So you take sigma 1 to be where the first 2 strands cross, and the remaining strands are vertical. And sigma I, you have the ith and I plus first strands cross, and the remaining strands are vertical. And sigma d minus 1, all the strands are vertical except the last 2 strands cross. Okay, so these are generators of BD. Why are they generators of BD? Well, if I give you d strands that go from bottom to top, you can just label it out so that one crossing occurs at each level, and you would write any braid as a word in these generators and their inverses, okay, depending on whether the crossing is positive or negative. And so these generate BD, but what's more difficult is to show that there's a finite presentation, and Artin wrote down this presentation. The generators commute if I and j are far apart because the strands don't interact with each other, provided that absolute value of I minus j is greater than 1. And if I and j are adjacent, then they satisfy this braid relation. Sigma I plus 1, sigma I is sigma I plus 1, sigma I plus 1. So that was a result of Artin. And you can check the relations, but then showing that they generate all the relations is the hard part. But that's what Artin did. So this is a presentation of BD, and there's a special element in BD which is called a full twist. But what you do is you take the d vertical strands, which is just the identity, and you literally twist the bottom and keep the top constant. By 360 degrees, you twist the bottom. That should commute with everything, because if I take any braid, I twisted the bottom or I twisted the top, I can slide the twist across the braid. So actually, we call this delta squared. It's a square of some delta, which I haven't defined. But it's a full twist, and it actually generates the center of the braid group. So anything that commutes with everything has to be a power of this full twist. So this is just a quick point I'm making, because I'm now going to actually talk about the full twist and reference Lenny's question earlier, which is what is the monodromy around infinity? So actually it turns out to be this full twist. But let's to get to that, let's now sort of compartmentalize the monodromy. So we said it's a map from pi 1 to BD. But then the question is how do we understand this better? We may be able to see what happens to a generating set of pi 1, and then see what the monodromy looks like for the generators. So let's imagine our points P1 all the way up to Pk. And let's take a free generating set for the fundamental group of CP1 minus the P's. Okay, so I'm just going to draw this loop gamma 1 going around P1, a loop gamma 2 going around P2, and so on and so forth, all the way up to gamma k. Okay, there are many choices for such a generating set. I'm just picking one. Now let's try to understand what is the monodromy around each of these gamma j's. Okay, so this is actually really cool. I think this is first due to Zariski, but maybe I'm wrong. I don't know, but yeah, but I think so. So Zariski observed that you can capture whether it's a node, a cusp, or a non-degenerate tangency based on the monodromy around one of these curves. And it's a beautiful construction. So suppose P1 is a node. How can I find the monodromy around the loop? That's going to be something in the braid group. How do I detect it's a node? And this is what we do. We consider a general idea of an AN singularity. And my notation is one shifted from the literature. I'm just going to write it as something modeled by y squared equals x to the n locally. So for example, if n is 1, we're looking at something like y squared equals to x, which basically models a non-degenerate tangency to a fiber of the projection. If n is equal to 2, we're going to look at y squared equals to x squared, which is modeling a node. And if n equals 3, we're looking at y squared equals to x cubed, which is modeling a cusp. Okay, so these are a general family of singularities. And let's try to find what the monodromy looks like around one of these local models. So let's sort of take y squared equals to x. What happens? So if you take y squared equals to x, and you have this local model for a loop that goes around a non-degenerate tangency, this is y squared equals to x. Let's draw a small loop that goes around 0 in the base. Okay? We can write that loop as, how do we write a loop that goes around 0 in C? We can write it as x equals e to the I theta, where 0 less than or equal to theta less than or equal to 2 pi, right? And then if we solve for y, what does y have to be? If x is e to the I theta, well, y squared is x, so y is going to be plus minus e to the I theta over 2, right? Those are going to be the y solutions. And if we think about this, what happens as theta goes from 0 to 2 pi? What happens if you go around a loop in the base? At theta equals 0, you have the points minus 1 and plus 1 in the fiber. And as theta goes from 0 to 2 pi, you're going to rotate. Because at 2 pi, you're going to also get minus 1 and plus 1. So you're going to sort of rotate 1 and minus 1. This is the monodromy at this branch. And this is a game of musical chairs where two people are rotating in that way. You can represent that as two strands crossing, basically, in 3 dimensions. And otherwise, you can always perturb so that there are no other singularities in the fiber. And so then there's no monodromy around any of the other branches of C. So you're just going to get vertical strands for the remaining remaining branches of C. And in this coordinate system, you're going to get this as a monodromy, which, if you look at that picture, is just a generator, right? So the monodromy around a non-degenerate tangency is just a generator. But of course, I have chosen a coordinate system, and a different choice of coordinate system will give a conjugate generator. So the monodromy around a non-degenerate tangency is just going to be, let me just write it up here. It's going to be a conjugate of sigma 1, G inverse sigma 1G, for some G in the Braid group B. That's going to be the monodromy of a non-degenerate tangency. And all the generators are conjugate to each other. So I'm just picking sigma 1. And of course, you can keep going. So you can ask, what is the monodromy around a node? And it's a similar computation. If I do a node, I'm basically going to get y squared equals to x squared. I say x equals e to the I theta. And then I just solve for y, and y is going to equal to plus minus e to the I theta. That's going to be the solution for y. And you see here, it's plus minus e to the I theta over 2, so it's going at twice the speed here. So instead of being sigma 1, it's going to be the square of sigma 1. So we're going to get the monodromy of a node is G inverse sigma 1 squared G for some G in BD. Okay? And you can keep going. I guess you can see the pattern now. For an AN singularity that looks like y squared equals to x to the n, the monodromy is going to be G inverse sigma 1 to the ng for some G in the Braid group. Okay? So some conjugate of sigma 1 to the n, which we call the nth power of a positive half twist. So we understand something about the monodromies around these loops. We now want to understand the monodromy of the curve. Okay, so how do we do that? Each of these loops will have a monodromy, which I've just explained is going to be some conjugate of sigma 1 to the n. Then, to go back to Lenny's question, what is the monodromy around a big loop that goes around all the p's? So the product of all those gammas over there is all the p's, is a loop that goes around all the p's. So you're going to have this big loop gamma that goes around all the p's that I can sort of draw in this board. And that's like a loop going around infinity. And because we have chosen a trivialization of the bundle over CP1 minus infinity, that loop will have non-trivial monodromy. Yes?
Just to come back here, though,
Yes.
first example, I mean,
Yes.
with braids and in algebraic geometry, there's a notion of positivity.
Yes.
And so with the first one, you want the positive sigma 1,
Yes.
I guess, but you don't want the negative sigma 1.
Yes, that's right. Yes. Yes. So you're commenting, asking like that why it's not sigma 1 inverse, or
Yes.
I see. So that follows from the assumption that everything is intersecting the fibers positively and transversely away from that non-degenerate tendency.
Okay.
Yeah. So you have like a big loop gamma, and if you know gamma is null homotopic at infinity, right? So the monodromy should be trivial. But because we have made a choice, we have trivialized the bundle over CP1 minus infinity, we have to take into account the change of coordinates, as I guess Lenny alluded to earlier. And if you actually compute the monodromy, something I can do after the talk, it's a computation, it just actually turns out to be delta squared. It's a full twist. You can sort of see it intuitively by, the transition function of the dual of the tautological line bundle, is basically a full twist. So you can compute the monodromy around this big gamma to be a full twist. The monodromy around each of these gamma j's is going to be conjugated to some power of sigma 1. So in general, you get this beautiful group theory thing that is a factorization. So the monodromy around the big gamma is delta squared. The monodromy around each of these loops, we call them, let's say G1 up to GK. Gj is the monodromy around gamma j. They're all going to be some conjugate of some power of sigma 1. And this notation, which I've drawn is 3 triple lines, is representing a factorization in the Braid group. So delta squared is the product of the g's, but I care also about what the g's are. So I'm caring about the factors. And you get a factorization. This represents the monodromy of C. It's called the Braid monodromy factorization of C, or BMF of C. And then the question is, like, what if I chose a different system? I made choices here, right? What if I choose a different generating set for pi 1? Instead of gamma 1 through gamma k, I'm going to get a different factorization. And you can actually understand algebraically what that factorization will look like. It will basically be generated from these elementary moves you can do to the first factorization you get. So you're essentially going to be doing handle slides on the gamma j's. So to get a different, sorry, what's the question?
Yeah, so
Yes.
just to make sure I understand,
Yeah.
what that means is that delta squared is equal to, G1, sigma 1 to the N1, G1 inverse. G2, sigma 2 to, sigma
N2.
1 to the N2.
G2 inverse. Yeah, all the way up to G. Yeah, exactly. Yes. So we know something about the factors. That's right. Yeah. That's right. That's a good comment. Thank you. And yeah, so what I was saying is that suppose we choose a different free generating set, a different choice of gamma 1 through gamma k's. You do these moves on the factorization to get the other possible factorization. So the move looks like the following. It's what's called a Hurwitz move. So if I have a factorization of something, right? K things multiplying to something, I can change the factors without changing that something, the product. And how that looks like is I have G1 all the way up to Gj plus 1, Gj inverse, comma Gj, dot Gk. So if you look at this, Gj plus 1 is the same as Gj plus 1, Gj inverse Gj, right? So I'm not changed the product of the factors, but I have just changed these two factors, these adjacent factors. This is what we call a Hurwitz move. And there's a symmetric version of it, which you can also do, that doesn't change the factors. And if you keep doing these moves to a given factorization for a given free generating set of pi 1, you will get all the factorizations of the fixed curve for all the generating sets of pi 1. And so this is what is called Hurwitz equivalence. Yes, Lenny?
Oh, so the g's are the conjugates of the powers of sigma 1,
Yes.
not the things that you're conjugating by to get based on this.
Yeah, exactly. Yeah, that's important. Yes, that's right. Yeah. Yeah, thank you. Yeah, that's true. Okay, so you have these Hurwitz moves, and then a corollary of Kharlamov and Kulikov's theorem, the takeaway of Kharlamov and Kulikov's theorem, is that the Hurwitz equivalence class of a Braid monodromy factorization, the Hurwitz equivalence class, this chalk has died, so I'll use a new one, Hurwitz equivalence class of a Braid monodromy factorization, or BMF, of our curve C, uniquely determines the isotopy class of C. Uniquely determines the isotopy class of C. So what's the takeaway of this? So in principle, yes?
So this Hurwitz equivalence, isn't that just the same as the equivalence under the action of the Braid group on
Exactly, yes.
the free group? Yeah.
Exactly, yeah. So that's another way of saying it. The Braid group acts on the fundamental group of CP1 minus the p's, and the action will generate all the free bases for the pi 1. And elementary Braid, like as generator, acts by this Hurwitz move. There's one other thing I should mention is there's also the choice of trivialization of the bundle, which I talked about earlier. That gives an overall conjugation of the factorization. So because delta squared is central, conjugating delta squared will not change it, but it will change the factors, and that gives you another BMF. But that's a very beautiful way of putting it. Actually, the Braid group acts on factorizations of any element in any group. So a braid group is kind of universal in that sense. These moves give you a braid group action on any factorization in any group, or the set of factorizations of a fixed thing in any group. And then the Hurwitz equivalence class of the BMF of a curve determines the isotopic class of C completely. What's the takeaway of that? Suppose I have a curve, I compute a BMF. You have a curve, you compute a BMF. If we want to show it's isotopic, we have to find a sequence of these moves that goes from one to the other. That's the takeaway. But how do we actually do that? So this is the problem. So I've developed new techniques in the braid group to solve problems like this. And in particular, get new results on the symplectic isotopic problem. And I'm going to state the first of my results, and it's actually on the right board over there. So I'm going to go to that. So this is a paper, it's on the archive. It's called The Complete Classification of Isotopy Classes of Degree 3 Symplectic Curves in CP2 via a novel algebraic theory of braid monodromy. And the result is the following. What we do is we take a degree 3 symplectic curve in CP2 with only AN singularities. Okay, so nodes, cusps, and other higher order y squared equals x to the n if you like. Now, if I have a curve and you have a curve, and our curves have different numbers of nodes, we cannot be isotopic to each other. So the first primitive obstruction for two curves being isotopic is they have to have the same number of singularities for each kind. Right? They have to have the same number of nodes, cusps, etc. So we define eta n of C to be the number of AN singularities in C, and we define a tuple for the curve to be eta 1 of C, comma eta 2 of C, dot, 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 comma eta n of C, where eta 1 of C is the number of non-degenerate tendencies, eta 2 of C is the number of nodes, eta 3 of C is the number of cusps, etc. So
new, not eta.
Yeah. I don't know the Greek letters. Thank you. Yeah, okay. Yeah, maybe I'll just call it. Okay, I'll try to call it new. Okay, if I forget, like, okay. So nu of C uniquely determines the isotopic class of C. So that primitive obstruction is complete. And secondly, in all cases, C is isotopic to something that satisfies a polynomial equation. Okay, so that's the content of this first of my main results. And I'm going to now give you some special cases. So to understand a result, you want to understand what the special cases are. So here are some special cases. What if C is just smooth? Okay, so if C is smooth, then C is isotopic to a smooth cubic. That's a special case. Now, you may remember that earlier in the talk, I said Sikarav refined Gromov's techniques 20 years later to show that any smooth degree 3 curve, symplectic curve, is isotopic to an algebraic curve. So this was already known by Sikarav, but purely J-holomorphic technique methods. But my proof recovers that purely algebraically. And there is a model factorization for delta squared in V3, which looks something like this. It's the simplest kind of factorization you can write down. It literally does not have any conjugates. Like going back to what Adam mentioned earlier, in principle it can be a conjugate of sigma 1, a conjugate of sigma 2, etc. It's just everything is unconjugated. But if you give any factorization where everything is like G inverse sigma 1G, then H inverse sigma 1H, etc., I can reduce it by Hurwitz moves to get it down to this one. So that's the way I prove that any smooth degree 3 symplectic curve is isotopic to your favorite smooth cubic, given by a polynomial in CP2. And there are other special cases, several others. So what if C has one node? So if C has one node, then C is isotopic to a nodal cubic.
Excuse me, ordinarily, an AN singularity is y squared equals x to the n plus 1.
X to the n plus 1, yes, that's right. Yeah, I mentioned that I shifted it up. Like, yeah, that's right. So C has one node, C is isotopic to a nodal cubic, which in affine coordinates is given by y squared equals x squared times x plus 1, looks something like that. You can write down a model BMF, braid monodromy factorization here as well. I can just sort of show you if delta squared is sigma 1 squared, sigma 2, sigma 1, sigma 1, sigma 2. Anything is Hurwitz equivalent to that thing. Anything where there is one node. You see the node as a sigma 1 squared. But in general, it can be any conjugate of sigma 1 squared. And so this was a result of Chisini using J-holomorphic curve theory. But I prove it completely algebraically. Then there is the case of one cusp, which was, again, known by some refinements of Gromov's theory of pseudoholomorphic curves. It's by Oda Ono. So all these results by Sikarav, Chisini, and Oda Ono, I unify them in the sense that I give a proof that proves all of them simultaneously rather than using different techniques in each case. And also the proof is completely algebraic without using J-holomorphic curve theory. You have other special cases. So you have two nodes. what if a degree 3 curve has 2 nodes? Well, then it's isotopic to the transverse union of a conic and a line. That's the model in algebraic geometry. If you have 3 nodes, it's going to be isotopic to like this kind of triangle, like 3 lines transversely intersecting in distinct points. And then you have other cases. You have a tack node, which then corresponds to a conic and a tangent line. And so these are special cases of the main result that I've written down here. What I'm going to also mention is this point that you may ask, what if I have a curve with 2 cusps, right? Why isn't that possible? So this is like an application of, for example, Bézout's theorem. So Bézout's theorem in algebraic geometry, traditionally, like, if you have, like, suppose you have a curve with 2 cusps, suppose it's C, you have 2 cusps, say P and Q, what you can do is, suppose this happens, right? Suppose a degree 3 curve had 2 cusps. It cannot. But if it did, you just draw a line through the 2 cusps L, through P and Q, and Bézout's theorem tells you that...
Bézout's theorem.
Bézout's theorem. Bézout's theorem. Okay, thank you. Yeah. So Bézout's theorem tells you that C intersection L is equal to the degree of C times the degree of L, which is going to be 3. But if you add up the multiplicities of the intersections at P and Q, that's going to be greater than 3 because they're cusps. So in particular, it violates Bézout's theorem. But you can also prove this purely algebraically. So this is another special case of this result. When I say that C is isotopic to an algebraic curve, I also say that, in particular, I prove that you cannot have a factorization of delta squared where you have 2 cubes of a generator, 2 conjugates of cubes of a generator. You cannot have a factorization where you have a conjugate of a cube of a generator and a conjugate of a square of a generator. In other words, you cannot have a degree 3 symplectic curve with a node and a cusp. You cannot have a degree 3 symplectic curve with 2 cusps, etc. So this recovers what we know by Bézout's theorem in algebraic geometry and also applies to the broader symplectic category, but it's a different way of proving that. So I'm going to I keep going, so I'm just going to, the last few minutes, I'm just going to give you a quick idea of how we approach this kind of problem. It's very group theoretic. And then I will give and sort of like the second of my main results. So this is just going to be a quick overview. I'm not trying to prove it. It's a paper on the archive. It's about 100 pages, but it's designed to be very accessible. You don't have to know Braid groups or algebraic curves to read it. So I encourage you to look at it and ask me questions. I'm happy to talk about it. But just give you a quick 2-minute overview or 3-minute overview of how we approach these kinds of monodromy problems. So in principle, we're trying to study factorizations of delta squared into these conjugates of powers of generators, right? So how do we do this? So the first step is just write out what we know. What we know is that delta squared is g1, g2, ... gk. And we want to glean something from this equation. We know this equation is true. We want to then say that we can find a sequence of Hurwitz moves to reduce the original factorization down to a model one, which I've written in some cases on that board. So we want to understand, why is this equation true? How is it realized exactly? I mean, this is like all of math, like understanding why things are equal in a way. So why are 2 things in a finitely presented group equal? How are they equal? So if you have a presentation, what that says is that if you write each of delta squared and g1 through gk as a product of words in the generators, you have an equality of 2 words. And if you have an equality of 2 words, you know they have to be equal by a finite number of applications of relations, conjugates of relations, introductions of symbols of the form XX inverse, or cancellations of the form XX inverse is the identity. It may be that you have to introduce these XX inverses in random places, and then only you can see a relation that you can apply. So in principle, the equality can be realized in a complicated way. And even if you can understand how the equality is realized, you then have to do moves on the level of factors. So the equality is realized on the level of generators, but factors are big chunks. So you then have to do the moves for factors. So the word problem, which is understanding when words are equal, is in some sense much simpler than the Hurwitz problem, but it's a necessary step to understand the word problem. So what I do is develop techniques to understand this based on what Gassai did with the word problem. And what Gassai did is he showed that to understand this equality, what we can do is any dj, we can just write as if I give you a braid, right, what can you do? You can write it as a product of the generators, but it may be a mess. It may be something like this, where the generators are intertwined with negative and positive powers, which we don't want to deal with really. But Garside told us, and this is actually a very simple and neat argument, Garside proved that you can actually write it in the form where the beginning has only negative exponents, and the ending has only positive exponents of the generators, and the negative exponents of the generators multiply to a power of this delta. And the positive exponents of the generators is what's called a positive braid, a product of positive powers of the generators. We call that a positive braid, and positive braids form a monoid. So you can collect the negative powers to one side, and then that equation over there basically becomes delta squared equals delta to the k1 tau 1 dot dot delta to the kn tau n. And you can then sort of move all the deltas across, and the taus will change, the indices of the generators will change, but otherwise you can characterize what happens. And when you do that, you eventually get an equation where you have a non-negative power of delta is equal to a product of positive powers of generators. And this equation has no negative powers. And in fact, an equation like this with no negative powers, you can realize by relations that don't have negative powers. So you can just literally see the Artin relations without introducing inverses and go from one to the other. The very short story, what I do in my paper is I develop a theory of equations to understand things of this form. And I give a new characterization of conjugacy, an explicit, explicit characterization of conjugacy classes of the form G1 through GK, which are conjugates of powers of generators. So I explicitly write down what their Gaussian normal forms are, and I combine those two to solve that problem. I'm just going to end the talk by stating the second of my main results is the last thing, because this theory is not special to B3, but in the case of B3, I handle the case of singularities. But I have the following general result in an upcoming paper, that if C is a smooth symplectic curve in CP2, so if C is a smooth symplectic curve in CP2 with no restriction on the degree, then C is isotopic to an algebraic curve. C is isotopic to an algebraic curve. So this recovers the known results due to Siebert and Tian, independent of Gromov's theory of pseudoholomorphic curves, but also extends it to all degrees. So I will end the talk there. Thank you so much for listening. Yes?
Yeah, I got a question/comment. So if you have a situation like you have, where you've got this open subset of P1,
Yes.
and then you've got a trivial line bundle over it,
Yes.
and you've got some branch cover sitting in there,
Yes.
that corresponds to a polynomial with C infinity coefficients. Because
Okay.
on every fiber you'll have D numbers, and you just take
Yeah,
the
yeah.
elementary symmetric functions in them,
Yes.
and they give you the coefficients of that polynomial.
That
So
makes
this
sense.
is going back to Artin's original paper on braids.
I see.
He wanted to understand monic polynomials. This will be a monic polynomial with
Yes.
coefficients of continuous functions. And then you look and see where they have distinct roots. That's
Yes.
the part you're looking at, and that's
Yes.
equivalent to a map from, say, your open set U
Yes.
into it's the configuration space of D points in C. So that's
Yes.
just so you've got a C infinity map in there, but if you have an algebraic, and it'll have certain properties close to the discriminant locus, it'll remain bounded.
Yes.
So then, if you have an algebraic curve, that map will be holomorphic.
Yes.
So now your question appears to be whether that C infinity map
Yes.
is isotopic, maybe via a special class of isotopies, to a holomorphic map.
Yes. That's very interesting.
So can you do, yeah.
That's very interesting. I never thought about it.
Yeah, and also maps of U, homotopy class of maps of U into that space
Yes.
is just equivalent to conjugacy classes of maps from phi 1U into the braid group, which is exactly
Yes.
what you're looking at.
Yes.
So it seems like that would be a good thing to do, is to look at.
Yeah, that's very, very interesting. I haven't thought about it that way. So I don't know if I have anything intelligent. You've already said the intelligent things that you said about that. I don't know if I have anything to add, but that's very interesting. Is that something that you think people have looked at before in some other
I have
context?
no idea whether
Okay.
people have looked at it in this context, but
Okay.
certainly Artin's original paper on braids was something like the 1920s.
Yes.
But I mean, people have written a lot about braids and polynomials.
Right, yeah. Yes.
I think you mentioned this at the end. The reason for the restriction to degree 3 is just because B3 is easier than B4.
Wait, which restriction, sorry?
That it has degree 3.
I mean, you're asking, wait, what? Yeah, I don't understand, sorry.
Why the restriction to degree 3?
Oh, I mean, degree 3, like, I mean, this is like, the way I work on this is like a first testing ground, but already like, the results were like, you know, using Gromov's theory of pseudoholomorphic curves took a long time to prove and were like important open questions. So even in that case, it's a challenging question, but it was a testing ground to try to do everything algebraically, so that's where I first started off with.
And what would be the problem in doing degree 4?
We mean, what are the extra difficulties when you go
Yes.
to 4? Purely algebraically? Yeah, so I mean, that's something that, I mean, more or less the techniques generalize. There are certain techniques where you need to refine them slightly. So when I was thinking about this, like, I have like a sequence of statements that solves it in degree 3. And then you can ask whether each statement generalizes for all degrees. So many of the statements do, and the proof is more involved. Some of the statements don't, but there's a weaker version of it that still suffices for the end goal. And so then I have to establish that weaker statement. So that was the process that I took from going from degree 3 to degree D. But I didn't consider the singular case in degree D. But in degree 3, I considered all possible singularities. Yeah.
If you have like a symplectic four manifold with a Lefschetz vibration
Yes.
and a symplectic curve inside of there, can you
Yeah.
play a similar game where now you're looking at some properties of some mapping class group of a surface with some functors?
Yeah, this is a good question because like, so I mean, you can define these monodromies of curves in like general ruled surfaces and like Isotopy surfaces. I haven't thought about it, but you can do the same game. For like Lefschetz vibrations, the thing is the mapping class group of a closed surface, some nice properties go away. So maybe to be very crude, like when I talked about like we want to understand, it comes down to understanding how this equation is realized. So in the mapping class group, there are more relations. So there are more ways this equation can be realized. So saying that you have an equality is a much weaker statement. So it's a bit harder to do. It's just I haven't thought about it, but I imagine in general also it can be very hard. But for braid groups, I mean, even then you have relations, but at least I thought about this case more. But it's a good question. I mean, in the hyperelliptic mapping class group, everything that commutes with the hyperelliptic involution, that's very closely related to a braid group, and you can do the same things. But yeah.
Probably the same question, because I read your like abstract saying that classification of the plane curves and symplectic manifolds,
Yes.
right? So I was wondering if there is a direct consequence of this theory on classification of the symplectic manifolds that you
I
can
see.
state like topology.
I see. I mean, if you have a symplectic 4 manifold that has a branch covering where the symplectic curve satisfies any of these hypotheses, it's smooth of any degree or it's degree 3 with only these nodes and cusps, then you can say it's a Kähler manifold. Then in principle, the classification of symplectic 4 manifolds, in principle, you can write everything down braid group theoretically. But I guess my title and abstract was just like a general, like, as I sort of started off the talk with talking about symplectic 4 manifolds, like a general principle that we can approach these questions via braid groups. I don't have any other concrete results to say otherwise.
Yeah, just staring at this, I mean, that theorem isn't true for degree 6. So for instance, you can have a sextics with 6 cusps
Yes.
on a conic and not on a conic, and they're not
Yes.
isotopic.
Okay. Wait. Can you say that? So you have sextic with 6 cusps. 6 cusps.
Sextic with 6 cusps.
Okay.
So there are 2 kinds.
Okay.
They're 2 different.
So one on a conic surface, and what do you?
No, on a through a conic plane curve.
Okay, through a conic plane curve. Okay. But what do you mean by? You mean there are 6 points on the conic, and
There
you're
are
drawing
6 points
okay.
on the conic
Okay,
which
I see.
are cusps with
Okay.
a plane curve.
Okay.
But you can also have a plane curve with 6 cusps,
Okay.
and they are not on a conic.
Okay.
This is classical. Zariski knew this.
Okay.
And
they're not
so
isotopic.
those are not isotopic.
Okay. Yeah.
So I have just something to keep in mind.
Yeah, no, I guess like Moiseson also constructed, like, as I sort of said, like curves with many cusps that are not isotopic to any algebraic curve. So it fails when you have cusps, and even, it definitely, like, you cannot generalize these results to like high degree curves with cusps. But in degree 3, or it's not so much the degree 3, it's just as long as the number of cusps is small, I think the general principle is you can do it. But as soon as the cusps become a larger number, then it becomes hard, and it fails,
Any other questions?
Well, I'd also be interested in knowing Zariski's argument, but maybe after the talk.
Okay, let's make